Good afternoon, everyone. Uh, am I audible?
Yes, ma'am.
Okay. I'll start sharing my screen. Please let me know if you can see it. And we'll wait for a couple of more minutes, then we'll start. Is it fine?
Yes, ma'am. No problem.
Okay. Please let me know if you can see my screen.
Yes, yes, yes.
Okay. Okay. Is it still visible?
Yes, ma'am.
Okay. 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 So I think I can start now. Hello, I am Shreya and I am the TA for this session. So I hope you all followed from week 1 to week 4. Is there anyone, who did not follow week 4 lectures before today's class? Okay. So it seems you have followed week 4. Any doubts in the previous doubt clearance sessions and problem solving sessions and anything else?
No, ma'am.
Okay. Alright, so I'll start today's problem solving session. So before starting, I'll just recap on what we have learned so far. So we have learned how we can fit a simple linear regression where my number of predictors would be how many?
One,
Yes,
two.
one. Number of
Yes,
predictors.
yes, yes.
Predictors would be 1, that is number of x's to be very precise. Yeah, so we have learned when we have one predictor and we are trying to find out the relationship between a dependent variable based on an independent variable, we visualize by a scatter plot, we fit a linear regression line. And how do we fit it? The main motive is to minimize the residual sum of squares. We write down the residual sum of squares, we differentiate with respect to the parameters of our model, we get our normal equations, and then we solve all those normal equations to get the estimates of the unknown values. Now there was one question in the discussion forum. I would want to address that. See, if I write something like this, so the question was, what is the difference between these estimates, I mean these values beta naught, beta 1 and beta naught hat and beta 1 hat. So we are assuming, based on our observations on y and x, we are assuming that y may be related to x based on this model. This could be the relationship where this epsilon is the error part which our variable cannot explain. So essentially, when we are saying beta naught and beta 1, these parameters are unknown, and whenever we are giving something hat, it means these hat things are estimates of the unknown parameters. So this is the difference between these beta naughts and beta naught and beta 1 hats. Whenever we are giving some hat thing, we are estimating the unknown parameters by which the y's, the dependent variable, and the independent variables could be related. Is this clear?
Yes.
Okay, so I'll just move on. So we saw how we are fitting a linear regression. Then the technique I just told you, you just write down the residual sum of squares, you differentiate, we do partial differentiation with respect to the parameters, we get normal equations and we solve them to get the estimates of our regression coefficients, that is beta hats. So once we have the beta hats, we can get our predicted values, and from there we can also compute the residuals and perform subsequent calculations. So we have seen some of the properties of the regression coefficients, in the sense that how they can be a linear combination of the observed y's, what are their expectations, and what are their variances, and what distribution they follow. These all we have learnt and seen in the previous classes. We have also solved sums, and then we have also tested the significance of a regression model, whether the predictors that we have taken are actually having any significant effect on the dependent variable. So such tests of significance also we have done, and as I was saying, that testing of hypothesis of single the regression coefficients h naught beta not equal to 0, h naught beta 1 equal to 0, these all also we have done. And we've also seen how we can calculate the confidence intervals and the prediction intervals. So this was all about simple linear regression that we have learnt previously, and then similarly we have learnt all of these for multiple linear regression as well. It's just an extension of the it's an extension of the simple linear regression problem. So this much we have done. Now when we are talking about a multiple linear regression problem, there could be several predictors. So if in a real life scenario we could have many number of predictors, so our job is then to select a subset. such that our variation in our dependent variable is can be captured as much as possible by our selection of the predictors, because uh, these we want something which is easy to use, and some dependent variable could be related to multiple factors. Now there could be problems in terms of cost, in terms of data collection, in terms of data processing, if we keep on adding predictors which we think are relevant. So in that scenario it is very important to select a subset of predictors which are going to uh, explain the variance in our dependent variable as much as possible. So in week 4 we have learned how we should be choosing those predictors from a large pool of possible predictors. So what essentially we have learned are variable selection techniques. So in this week lectures, if you've gone through, sir has discussed 4 techniques. So one was, anybody, what were the 4 techniques? Anybody remembers? Nobody?
Forward selection, backward elimination.
Sorry?
Forward selection.
No, that I am not. That is definitely one of the techniques of variable selection. But when we are doing all possible regressions, so what were the 4 techniques that were discussed? The metrics, to be specific. So one was the R square, which is nothing but the coefficient of determination, which was the proportion of variance explained by, proportion of variance explained by a regression, that is actually my R square. So this one was one of the metrics, and then the second one was adjusted R square. The third criteria was minimizing the residual, mean square residual, and the fourth one was Mallow's CP. So these were the 4 metrics that were discussed in this week lectures. Of course there are other variable selection techniques like stepwise regression, forward selection, backward selection, that I'll discuss next week. So this week what was discussed, that if we can possibly fit all possible regressions from our pool of predictors, then from that set of models, how am I going to select regression equations which or variables which are which can maximally explain the variance in our dependent variable. So today I'll solve some problems with respect to the techniques that we have discussed this week, and hopefully you'll be able to follow. So is it fine? Shall I start with the techniques?
Yes.
Okay. So this is the first question. So I have also said before that predicting a price of a house could be considered as a multiple linear regression problem, because it could depend on a large number of factors. So here, for the sake of this problem, I have selected 4 such parameters or predictors on which the price of a house could depend on. So one is this age of the house, whether it's a new one, newly constructed one, or an old one, the floor area, the locality where it's present, and say distance from the nearest hospital. So data was collected from 13 houses, and we have reported the residual sum, we have calculated the residual sum of squares for all the possible regressions. So how many possible regressions can we have with these predictors? So see, when we are not selecting, we are always having this beta 1 term included. So this could be my model when none of the predictors are selected. So out of 4 predictors, I am selecting none. If I select one variable, let's say and so on and so forth. So how many such regressions can we fit with one variable? Out of this pool of 4, we are selecting one predictor. So similarly, if we select 2, then we have these many regressions. And then if we select 3 predictors, then we have these many. And finally, if we select all predictors and fit the model, then we have these many regression equations. So if you just sum this up, then it comes to 2 to the power 4, that is 16 equations we would have. That is all total number of possible regression equations or models. Any doubt here why it's 2 to the power 4? Anyone?
No.
Okay. So once we have determined that how many possible regressions can be fit, here we have been given with 16 residual sum of squares, which has been calculated based on 13 houses. So these are the 16 models. Okay, this none is y equal to beta naught plus epsilon. This one is y equal to beta naught plus beta 1 x1 plus epsilon, and so on. And these are the residual sum of squares which we have obtained by fitting each of these models, and then again getting the estimates, calculating the residuals and their sum of squares. So this information is already provided to us. Now the question is, what will be the coefficient of determination, that is r square, for the model this one? So any idea how we should proceed? So initially, first things first, what we are fitting? We are fitting x2 and x3. So our model is basically this one. Fine. Now we are to find out the coefficient of multiple determination based on this one. So if we just write down the ANOVA table, then these are our degrees of freedom, sources of variation, sum of squares. Let us write this much only for now. So there are two sources of variation, the regression, the residuals, and the total. So here our n, total number of observations, is 13. So what will be my total df? This will be n minus 1. Why? Because summation yi minus y bar is equal to 0. We have this constraint. Out of the n y's, we can only choose n minus 1 y's freely. The rest will be chosen as per this criteria. So we have n minus 1 df, the total degrees of freedom. Again, for residuals, how many degrees of freedom do we have? N minus the number of parameters or the number of normal equations that we would have. So here you see we have beta naught, beta 2 and beta 3. So we have 3 parameters. So if n is 13, our total degrees of freedom would be 12, and the degrees of freedom of residuals would be 10. And due to additivity property, the regression df would be 2. Now from this table we have the residual sum of squares as 274.34 when we are fitting x2 and x3. So this one would be 374.34. Now for R square we want SS regression by SS total. We have this information. Now if you observe carefully, this model y equal to beta naught plus epsilon, this is without any regressor. So whatever is the residual sum of squares here, because here SS regression is 0, the entire thing is only SS residual, because we are not fitting any of the it's not dependent on any of our predictors. So there is no such regression line over here because there is no predictor. So this value that we have as residual is essentially my sum of squares, is my total sum of squares. Okay. So is this part clear? Why this is the total sum of squares? Hello?
Yes, ma'am.
Okay. So once we have this total sum of squares due to regression is just we just need to subtract 374.34 from this one. So if you do the calculation, and please let me know if I am correct or not, you would get this as 2140.53. 7841152. Okay, then the value of r square would be 2140.53 by my total sum of squares, that is 2514.87, and this would come out to be approximately 0.85. This is the answer. Any doubt on this question? Okay, I am assuming there is no doubt. So similarly, if we are to find out the coefficient of multiple determination for this model, beta 1 x1 plus beta 2 x2 plus beta 4 x4. So here again, if we draw the ANOVA table, Then here the degrees n is our n is 13. So total degrees of freedom would be n minus 1, that is 12. Now here we have how many parameters, how many normal equations would we have? One for this one, one for this one, one for this one, one for this one. So 4 normal equations or parameters we have unknown. Therefore our degrees of freedom would be n minus 4, that is 13 minus 4, it would be 9, and degrees of freedom due to regression would be 12 minus 9, 3 predictors, 3. Okay, so in this scenario the sum of squares due to residuals we will again compute from this, get from this table x1, x2 and x4, that is we are looking at this one. So if we fill in, this will be 43.24 and the total is this one, 2514.87, and due to regression we will get it like 2471.63. So then R square would be SS regression by SS total, that is 2471.63 by 2514.87. This would be 0.98 approximately. Is it fine? Even though we did not need the degrees of freedom calculation over here, but it is very important to note that this degrees of freedom is very important and it will vary with the number of parameters that we are estimating. So this concept is very important and it should be very clear. Okay, so I'll move on to the next question. Here again I am asked to calculate based on the values of R square which one of the models is preferred. So the first and foremost thing that we should note is that R square increases with the number of predictors. So as we keep on adding more predictors, the value of R square will keep on increasing. Now since here we have uniformly 2 predictors for comparison, we just cannot directly look at it and say that okay, this is the best one, because all of these are 2 with 2 predictors. So what will we do? Nothing, we will just calculate the R square for each of the models. So here we have 3 models. This one is based on x1, x2, this is based on x2, x3, and one based on x3, x4. So R square we know is SS regression by SS total, but alternatively we can also write it as 1 minus SS residuals by SS total. Is this fine?
Yes, ma'am.
Yes, thank you. So directly also from the table we can get this value. So our SS total we know is this thing 2514.87, and SS residuals is x1 and x2, that is this thing. So we have 45.77 by 2514.87, and this was come to something around 0.9818. Please check the calculations. Okay, I might be wrong, but this is the technique by which you should find it out. Then for x2 x3 similarly we can the r square value is 1 minus residual sum of squares when fitting x2 and x3. So x2 x3 is this one, 374.34 by 2514.87, and we calculated this earlier, it came out something as 0.85. Similarly for x3 x4 this should be 180.01 divided by 2514.87, and then this will come out as 0.9284. So out of the three, which one is maximum? Maximum proportion of y is explained by these two variables x1 and x2. So if we have to choose based on the value of r square, which of the following models would we prefer? We would prefer model A, because here the r square value is the highest among these three. Okay, so next I'll the previous question was clear, I hope. Okay, fine. So this one I have been asked to calculate the value of Mallows statistic, that is CP. So in the lectures we have seen that Mallows CP is written as sum of squares due to residuals for the model with p parameters divided by mean square residuals when we are fitting the full model minus n, where n is the sample size, and plus 2p, where p is my number of unknown parameters. This is the formula of Mallows CP. Now we have to use this and get its value based on the figures in this table. So let's just start with it. So here, what is the value of P for this model? Anybody? P is the number of unknown parameters. So what is the value of P? Am I audible? Okay, I hope I am audible. So here, since we have 3 unknown parameters, here our P is 3. Okay, thank you. So then CP for this model would be sum of squares due to residuals for these two, the model with these two predictors, by the sum of squares due to residuals due to the full model, that is x1, x2, x3, x4, by the degrees of freedom of full model minus n plus 2p. So if we just calculate from that section here, we had Cp equal to sum of squares due to residuals for x1 x4 by sum of squares due to residual full by df of the full model minus n plus 2p. So sum of squares due to residuals for by fitting x1 and x4 would be this value. So we have 65.99 divided by now. When we are fitting the full model, our sum of squares due to residual is this much. But what is my degrees of freedom for the full model? So see, the full model will be y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus epsilon. So in that case we have 1, 2, 3, 4, 5 unknown parameters, hence 5 normal equations. So our degrees of freedom for residuals in that case would be n minus 5, that is 13 minus 5 is 8. So we will have a DF full model as 8 minus 13, because that is my sample size, we have surveyed 13 houses, plus 2 into, and P was the total number of unknown parameters. So 1, 2 and 3. 2 into 3, 6. So if we do this calculation, then we would get the value of Cp as 3.911. You can do it and check it for yourself. Okay. So similarly, if we have been asked to find out the value of the Mallows Cp statistic for this model, then similarly we can write Cp equal to sum of squares residuals due to by fitting x2, x3, x4 by sum of squares of residuals in the full model by degrees of freedom of the full model minus n plus 2p. For this problem we have 1, 2, 3, 4. 4 unknown parameters, hence p is 4. So we will just replace with the values x2, x3, x4. That means this thing. We would get 77.25 by this full model is 48.38 divided by the full model has, as I was telling, 5 unknown parameters and the DF was, we calculated 13 minus 5, 8. So this one minus 13 plus 2 into 4. So if we just calculate this entire thing, we would get our Cp to be close to 7.77. Okay. So next, if we are to consider models involving 3 regressor variables. So now if I have to choose based on the value of Cp, which of the models would we choose? So when we are asked to consider models involving three regressor variables, which models, which of the 16 models should we use? Anybody? Okay, so if we have to choose a models involving three regressor variables, then we should focus on these models, because each of these models there are three regressor variables. Okay, so I'm sorry, just a second. So let's work on the first one, x1, x2, x3. Then Cp would be sum of squares due to residuals, this one 52.19 by mean square residuals from the full model, that is 48.38 by 8 minus 13 inverse 13 plus 2 into, now our P would be 4. Why? Because here we also have a beta naught term extra along with these. So 4 unknown parameters, P is 4. So if we calculate this thing, we will get it something around 3.63. Next, if we proceed to x1, x2 and x4, then Cp would be 43.24 by 48.38 by 8 minus 13 plus 8. If we calculate it, it will come something around 2.15. Then if we get the third model, then for this one Cp would be 51.67 by 48.38 by 8 minus 13 plus 8, then this would be 3.54. And the other one is x2, x3 and x4. So in this case Cp would be this would be so we have the Cp values of the four regression equations involving three regressor variables. So for C3, that is 4, we have 4 equations and 4 Cp's. Now whenever we are asked to choose based on the value of Cp, we should choose Cp in such a way that Cp is low and it is as close as possible to P. So in this case P is 4. Now why such criteria? Because when we have seen in the lectures as well that when we are fitting the full model, then Cp the graph will pass through the origin. So we should have points which are as much as close to this line. That would be our criteria of choosing the best model, and the value of Cp should also be low. So here we can see that since P is equal to 4, the value is also quite low and it's close to the value of P, that is 4. So one of our options is to choose or prefer this model over the other models as well. But I mean, if we are not focusing on that CP close to P criteria and we just want to focus on the lowest value, then we would choose this one. But it's advisable to choose a CP which is low as well as which is close to the value of P. So based on those criteria, we would choose this one as it closely approximates 4. Now there could be situations where it is a little dicey as to which variable shall we choose. So we can go ahead with the other methods like adjusted r square, CP, that mean squared, and from all these, if we compute and calculate and see which is giving us a better result, we can go for that. Okay, so the next problem I'll move on to. So here I have I'll just read the question. F1 given 3 denotes a partial f value. F value means f value from the f statistic. You remember when we were doing the ANOVA table and we calculated the f statistic to test out whether the regression was significant or not, MS regression by MS residuals, that was our f statistic. So that one. So we are denoting f1 given 3 as the partial f of x1 given that x3 is already in the model. Then what would be the value of f of 1 given 3? So if you remember the extra sum of squares techniques, then you would remember that the f statistic, it can be computed as sum of squares due to regression from the unrestricted model minus sum of squares due to regression from the restricted model divided by R, the number of restrictions in our hypothesis, by MS residuals from the unrestricted model. So all we need to determine here in this context is which one is our unrestricted model and which one is our restricted model. So unrestricted H naught would be this one, where x is also there given that x3 is also there. That is, if we have a model like this, y equal to beta naught plus beta 1 x1 plus beta 3 x3 equal to 0, plus epsilon, extremely sorry, plus epsilon, then unrestricted H naught is beta 1 equal to beta 3 equal to 0, and the restricted I'm sorry, just a second. So as I was saying, our model in this case would be beta naught plus beta 1 x1 plus beta 3 x3 plus epsilon. This is our model, because we want to find out whether this partial x1 given x3 is of any significance or not. So the H naught in our model, or the restriction, was beta 1 equal to 0. So from this thing it follows that our f statistic in this case would be sum of squares due to regression based on the unrestricted model, that is both are present, x1 and x3, minus sum of squares are due to regression when under the restricted model. So our restriction was beta 1 equal to 0. So the sum of squares due to regression will be only due to x3 because it is given that x3 is already in the model, and our R is 1 because that is the only restriction that we have, divided by MS regression due to x1 and x3. So this thing, it can be written as sum of squares total minus sum of squares due to residuals x1 x3 minus sum of squares due to total sum of squares minus residual sum of squares for x3 divided by ms, sorry, this will be ms residuals. This would be ms residuals due to x1 and x3. So if we do the calculation, so here we have f equal to ss t minus ss residuals due to x1 x3 minus SST minus SS residuals due to x3 by MS residuals x1 x3. So this SS total and SS total will cancel and we will get SS residuals due to x3 minus SS residuals due to x1 and x3 by SS residuals due to x1 x3 by df of the model with x1 and x3. So if we fit the model, our model was full unrestricted model was beta naught plus beta 1 x1 plus beta 3 x3 plus epsilon. So we had 3 unknown parameters. So df of residuals would be 13 minus 3, that is 10. So we just put the values here. So SS residuals due to x3 is this thing 2098.26 minus due to x1 and x3 1301.02. This is divided by 1, this was by 1, so it will remain as it is, by x1 and x3, this one 1301.02 divided by the df from the model fitting both x1 and x3, that is 10. If we do the calculation, we will get it something around 6.127. This is the partial value of f of x1 given that x3 is already in the model. So if we get a question, some questions like this, we should always write down the model first, then the h naught and the number of restrictions that we would have, and then based on this extra sum of squares techniques we should get the F statistic. Is this clear? Okay, I'm not getting any response, so I hope that it's clear. I'll just proceed to the next one. So here we have been asked to calculate the R2P bar, R square P bar, that is nothing but the adjusted R square. So the formula for adjusted R square is 1 minus R square was sum of squares and adjusted R square is nothing but mean sum of squares. So ms residual P by ms total. So this is nothing but 1 minus SS residuals P by this one would be n minus P because there would be P number of unknown parameters, and this would be SS total by n minus 1. So if we just rearrange, it would be n minus 1 by n minus P SS residuals due to P parameters by SST. So in this context our P is 1, 2, 3. So n minus P would be n minus 3, then this would be 1 minus 12 by 13 minus 3, that is 10. S is due to P. So our predictors are x2 and x3. So this one into 374.34 by SST was this one when none of the predictors were used, 2514.87. So this would come around 0.82. Is it fine? Hello? Okay. Okay. Fine. So if we are asked to find out the adjusted R square, then we should use this method, and we should also keep this in our mind that our adjusted R square is a better measure than R square. Why? Because R square will always increase as we increase the number of predictors, but this adjusted R square will not behave accordingly. So if the trade-off between loss of degrees of freedoms and the decrease in the residual sum of squares, the increase or decrease in R square, in adjusted R square, will depend on that. So it's not necessarily that we increase P and increase the complexity of our model, then our model will perform well. This adjusted R square puts a check on that. So between these two, R square and adjusted R square, if we are to choose a criteria, we should mostly opt for adjusted R square P, solely because of the reason that it does not increase by increasing the number of predictors, but R square will increase even if our predictors are irrelevant, if we keep on adding them to our models, the value of R square will increase. But it's of no use adding irrelevant parameters to our model. We should add it in such a way that the entire thing makes more sense. So yeah, this is a better measure. And the last question for today is the value of Mallow statistic for the full model. So the full model would be this thing, because we had 4 predictors and 5 unknown parameters. So here in this case our p would be 5, and we have seen that when in case of a full model, Cp is equal to p. So our answer is 5. Okay, so this was all about week 4, and in the next week we will learn about some more variable selection techniques and what we can use to choose our predictors, so that our regression is a better fitted regression line based on all the goodness, which variables are relevant, which variables are not, and how we should select variables if we are presented with a large pool of predictors. So I hope I was able to convey some of the concepts that was discussed, and if you have any questions you can ask me now, or you can also use the discussion forum to have any questions, and we'll try to address that. Okay, so thank you so much for joining. I'll just stop my presentation now, and we'll meet again next week.